All right. Good morning. Welcome to this course that we're calling IP Fundamentals. My name is P.A. Hansson. I'm working at for Global Knowledge. I have been doing that for the last 6 years now. And what I usually do is I do mainly Cisco teaching and some Nortel stuff as well. Datacom. Also, I don't know if you know anything about Global Knowledge, but we do also have our own courses that we develop. So I do a little bit of that as well. The course today is called IP Fundamentals. We're going to be talking about IP and the basics of IP. We'll also talk a little bit about the Datacom fundamentals. So we'll have some Ethernet basics in there as well. There's also a applied, or there's a new course, or not a new course, another course later on called Applied, where we'll talk more about the higher levels. So the slide that's on now is called You and the Networks. And it's a little bit about what we'll talk about and what we'll try to understand as we go along. So Datacom in general, IP specific. So this course will talk about the connection between your computer. We'll talk about configuration of IP and how IP works. We'll talk about the LAN, the local area network, which you're connected to. We'll talk a little bit about how it all connects together. And then in the applied course, and there will also be other courses where we'll go further up towards the applications and the implementation higher up, services and stuff like that above. The course today will start now at 9. We'll finish up about 4:30, something like that. We'll have a lunch break at some 15, 20 minutes past 12 for an hour. I'll try to make 1 hour sessions, so we'll have like a 10-minute break every 10 minutes. There's supposed to be about 50 people here, so I would like you to, if you feel comfortable with it, to ask questions. I'm used to working in a classroom with 10 or 12 people at the most. So I'm used to having questions. So if you just sit there and don't say anything, I'm going to be really confused. So please help me out by asking questions. Also, we're doing this in English, and it's not my native language, as you probably heard, as well as most of yours. Not have English as a native language as well. So if you don't understand what I'm saying, please don't hesitate to ask any questions. All right? All right. Let's start out then with the first chapter, which is about network basics. The course, by the way, is created from mostly different global knowledge courses that we have put together. This first chapter is called Network Basics. We'll go through the basics of LANs, WANs, and how they're connected. We'll talk about different computer and network devices. We'll talk a little bit about bandwidth and what the network protocol is. And all of this, which we'll talk about in this chapter, we'll go deeper into in other chapters later on. I'll start by asking you a question. What's the use of a network? Why do we have a network? Anyone? Anyone heard of network?
Sharing information.
Sharing information, very good. That's the key thing. And if you think about it, whatever your network is supposed to do, it's all about sharing information. It might be because you're working together with a group of people on a project and you want to share your documents. It might be because you want to surf to, I don't know, Aftonbladet website and look at what's been happening in the world. You might check the weather. You might need to patch something from a manufacturer, a software patch or something like that, or whatever it is. You want to share something with a colleague or a friend. Whatever it is you're using your network it's for sharing information one way or another. My main occupation is teaching network administrators how to administer the network. And I always used to say that the best working network is the one where there is no users. Because if you don't have any users, the network will work. Now, unfortunately, it's not much use for a network without any users. And as soon as you put users on the network, you're going to have problems. But that's what networks are for. So anyone doing software application or programming of any sort? Because I've been doing that previously. And no matter how you create or how you go through your program when you program it, and as soon as you leave it to a user, he's going to wreck it. He's going to find a way to do something to the application that you're not used to. You didn't think someone was stupid enough to do it, and they're going to wreck it. So that's why we have software bug testing. So the network is for sharing information one way or another, and that's what we're going to talk about. When we talk about networks, we split it into a local area network, or LANs, and wide area networks, or LANs. Where the local network obviously is your local network within your office or your home or wherever. And you use a wide area network to connect to remote places on other locations. It might be connecting Kista to Älvsjö, or it might be connecting New York to Sydney, or whatever. So we differentiate between local area networks and wide area networks. We're going to talk about mostly on a datacom level about LANs, because we're going to talk a bit about Ethernet and how Ethernet works, and also a little bit about wireless networks. So that's what we're going to do. But we differentiate between local area networks and wide area networks. This is a little timeline about networking. The first computer back in the 50s. There's some famous quotations from people. One that I really like from back in the 50s was there was a guy working with computers, and he said that he was almost completely sure that one way or another in the future we're going to have computers weighing less than a ton. He was almost sure of that. Some things have happened since that first computers. Back in the 60s and most part of the 70s and later, we have the T1s or the E1s, or the plesisynchronous hierarchies. We were having mainframe computers with stupid or dumb terminals connected to. Internet, which is a story on its own. Most people say that the work with the Internet, what we know now as the Internet, started out in the late 60s, 69 something. There's a computer network called ARPANET, which were the start of the Internet as we know it today. Lots of things happened between ARPANET and the Internet we know today, obviously. I'll get back to that later. Ethernet and token ring date back to the 70s. During the 70s and 80s, and part of the 90s, Ethernet and Token Ring were competing for what we're going to be using on the LAN. Today, if we're talking about wired LANs, it's almost completely Ethernet. Anything else you can disregard because there's so small installations. So if we're talking about wired LANs today, it's Ethernet. And that's what we're going to talk more about as well. PCs, late 70s, early 80s. X25, you heard about that. Then service, back in the 70s as well. IEEE is a standardization organization that is, I used to say, doing standards for anything electric, anything between a vacuum cleaner and a nuclear plant, anything in between. IEEE also has an 802 committee, and it's the 802 committee that is doing the standardizations for instance, for LAN, for datacom. 10BASE-T Ethernet, so the Ethernet that we know most, that you're most familiar with, perhaps, the 10 megabit Ethernet, using the twisted pair cable, that network cable you have connected to your computer, is also dating back to the 80s. Some cabling standards, frame relay, late 80s, ATM, early 90s, web browser, which was actually developed or thought about, implemented first in CERN in Switzerland. There are lots of people today that think that the internet and the web browser is more or less the same thing. You can do more on the internet, obviously, than surf. Ethernet has a faster cousin called Fast Ethernet, or were called Fast Ethernet when it arrived. It's 100 megabit. And then we have gigabit Internet, and also today 10 gigabit Internet. Ethernet, sorry. When you create your network, we're going to have some challenges, planning issues. There are lots of things that go into designing your network. One very important aspect is the planning. It's quite common today that we see networks that have grown over the years, perhaps 10, 15 years. And if you don't have a plan for growing your network, if your network starts getting older, in 10, 15 years, you're going to grow out of your plan. Or if you don't have one, you're going to be in trouble. So when you design a network, it's really important that you have a plan. In the more advanced courses we teach, IP planning and IP designing is a huge part of doing planning your network. So, obviously, performance, uses. There's a difference, obviously, as you're going to see on the latest slide, between what we used to do on the network 10, 15 years ago compared to what we're doing today. And it obviously has to do with performances and the performance on the network. It's really easy to create and build and design a network if you can use as much money as you like. Now, unfortunately, not many people have that opportunity. So obviously, when you design a network, you're going to have some budget restraints as well. Security, big thing. It's an interesting question, really. We're calling this course IP Fundamentals. Why is it that IP, why not IPX or DECnet or AppleTalk or another network protocol that is out there? How come we're using IP? Why is everyone so concerned with running IP? Why TCP/IP? Why not IPX? If you go back to the 80s and the early 90s, and you went to a datacom course, we were talking as much IPX as we were talking IP. How come everyone is talking IP? Now, everything is going over IP. Wherever you go, people say, well, and Ericsson is one thing of it. Everywhere you go, people saying, nah, we're not running anything. We're just doing everything over IP now. It's IP only. Which is, as you will notice, not completely true, because you need IP to go into something else. But we'll go over that later. Why IP? Anyone? Because it's much simpler than you think. Is it much better? Is it free? Why IP? I actually mentioned it just a minute ago.
It is the security aspect.
It is a part of it, but it's the other way around actually, because IP is an old protocol. IP in the internet is like this. The internet and IP are buddies. They grow up together. And that's also the reason why everyone is running IP. Because the internet is a TCP/IP network. So if you're going to be connected to the internet, you can't run IPX, can't run the Apple Talk, DECnet, or any other network protocol. You have to run TCP/IP. And that's the reason. Not because IP is much, much better. Not because it's free or anything like that. It's because you need it to be connected to the internet. And today, if you're not connected to the internet, you don't exist. Right? So simple as that. Which takes me back to the security concerns. Remember I said that the internet started out back in '69, late 60s. Very early, during the internet or the ARPANET network, they found out that they needed a new protocol, and that protocol is IP. So IP and TCP/IP is dating back to the early 70s. And back then, nobody knew about what we know today, about the internet and the size of the internet and the security concerns we have, the hackers and crackers and all of those people. It took way, I think it was back in '77, where they had 100 hosts on what was supposed to be the internet later on. 100 hosts, 100 computers connected to this ARPANET. And back then, nobody knew about the size this will take. So, therefore, IP and the basics of the IP, the start of IP, was created without any thought about security. And that's why we have to add on security as we go along. And that's why some of the protocols in the IP, TCP/IP protocol suite isn't very secure. And we have to fix that. We have to add things to it. So security concern, obviously, because, as I said previously, everyone's supposed to be connected to the internet. So if everyone's connected, which is a good thing, we get lots of information. But since everyone is connected, there are also other people there. My girlfriend, my fiancée, got one of those phishing emails yesterday. Anyone else got those from Nordea? Or supposedly from Nordea? There are actually people that fall for those kinds of things. So security concern, because we're connected to the internet, we need to take care of that as well. There are people, security people, that say the only way to be really secure is to not be connected to the internet. And to be honest with you, how many of you office workers actually need the connection to the internet for working purposes? Not that many. So now, the internet is not the only place for security concern, obviously. There are people saying that about 60 to 70% of all security breaches are from within the network, from your own suppliers. Yes. Yeah, that could be one reason. Yeah, sure. Yeah. Today, no. Not if you want to email someone outside your own organization, obviously. Yeah.
But within my organization as well, because we're not all of us are not connected to the same lab.
Yeah. But that's why.
Connect to different labs,
Yeah.
you have to go via the internet. So even though you don't need to talk to someone outside Ericsson.
You don't have to go via the internet. And most companies, if you go back 10 years ago, we were not connected. We used our own WAN services, or rather we bought WAN services from service providers. Now, buying WAN services is costly. So today, most companies, what they do is they get internet connection, and then they set up VPNs and use that because it's cheaper and you get more bandwidth. Today, probably right, we probably can't work without internet connections, right? Oops. Obviously, if you create a network, you should be able to manage the network. It should also be easy for the users to use the network. Another thing which we talk a lot about in the other courses is redundancy and availability. And especially today, because what we used to have a telecom network, and we used to have a datacom network. Now, if your datacom network broke, you can use the phone, you can call your colleagues, you can call your business partners, whatever. If your telephone network broke, which it basically never did, but if it did, you can still use your datacom network. Now, today, we're trying to do a converged network. We need to have, or we want to have, one network. And we're running IP phones, and we're doing everything over this converged network. Now, to do that, if that network breaks, what do we do? Mobile phone. If it's the same network, we might as well go home, right? So, availability and redundancy, to make sure that we have a redundant network that is always up. And most of you, I guess, is working with a telecom, or mostly has been working with telecom. And for you, that thing with availability is something that's always been there. I don't remember the last time I picked up the phone and it didn't ring. Well, I do now because I got an IP phone now from one of the service providers, and that breaks. But before, when we were all connected to Telia, it always worked, didn't it? But now we have a datacom network, and all of a sudden we're supposed to get used to it. It's not working. Sorry. We need to make sure that we got an availability and we got redundancy. The network then, obviously made up from devices, your computers, servers, printers, any other device you like to put on there. On top of that, we'll be running our applications, file transfers, emails, different kinds of images or voice and video stuff today. And the network itself, with the LANs and WANs we talked about, and the equipment that makes the network, so the hubs, switches, routers, and the cables and media that connect those together. We'll go through the difference between a hub, a switch, and a router as we go along. Obviously, different applications have different performances issues. There's a big difference between the data that we're sending on a network today compared to what we did 20 years ago. 20 years ago, it was numbers and text, ASCII-based. Today, we're sending voice, video, having telecom conferences, large, much bigger files, much more traffic, much more time-sensitive traffic. And obviously, there's a difference between sending different kinds of traffic. And today's network, if we're talking about that converged network, needs to be able to handle all of it. And that's one of the things that makes it kind of strange, really, that we're moving towards an all IP network. Because to be honest with you, one thing that IP really sucks at is quality of service, which is why it's been taking us so long to get to the point where we are now. IP in itself really is not a good quality of service carrier. ATM, if you've been working with that, that's super for quality of service. IP sucks at it. So we need to be able to add stuff to make it work. Also, since we are connected, as the lady up in the right corner said previously, we connect to different networks. We also connect our local area networks, which is relatively cheap to build. Most companies own their own lands. You can get quite a lot of bandwidth for not that much money. But if you want to connect Kista to Älvsjö or some other place, you need to go over a WAN connection, a WAN service. And those connections are usually bought from a service provider. And if you buy something from a service provider for going long distances, you're going to have to pay for it, which means that the WAN, you don't own it, and you pay for it, so the bandwidth is going to be less on the WAN links, which means that what you can do on your own LAN from within Kista, the Ericsson Kista, is not going to have the same capabilities, or you're not going to have the same performance if you try to do that between different places far away, because you're going to be able to go, or you're going to have to be going over the WAN, and you're not going to have the bandwidth there. So how well it will work? Well, it all depends, obviously. It depends on the application. It depends on the bandwidth, both on the WAN and on the LAN. And it also depends on any quality of service implementations that you or your service provider prefer both heavily implemented. Sending an email isn't that big a problem. It doesn't really matter if it takes 10 seconds or 15 or 2 minutes to send an email. But if you're sending a voice call, talking to someone over an IP phone, you're not going to be very happy if you're starting to get delays for 2 or 3 seconds at a time. So it all depends on what kind of application you're running. We'll get back to that later as well. What we'll look into a little later is the LANs. And what we want to do today is we want to have segmentation. It's not a good idea to have all 110 users on one single LAN because they're sharing the bandwidth. I want to go through with you later when we go into the next chapter about the Ethernet and how Ethernet has evolved. But what we want to do today is we want to have switches. We want to have switches that can handle something called VLAN. And when I say VLAN, I'm talking about the virtual LAN. We'll go through the wireless LANs as well, Ws as well, but VLANs and switches that handle VLANs, so that we can create segmentations between the users. There are lots of different reasons for doing that. I'll get back to that later. The LAN basics, obviously you got your different devices, your PCs, servers, printers, whatever. The most common network cable from a user perspective anyway is the UTP cable. It's that cable that you have to your desktop. Today, most commonly, it's the category 5 cable, which you need to be running 100 megabits Ethernets. UTP stands for unshielded twisted pair. So the cable consists of 4 pairs that are twisted 2 and 2 together, and then it's unshielded, so it's just a coating outside, not shielded on the outside of that. Relatively cheap, most common connected to your devices. And then they have a hub in there. Now, you're not going to be finding very many hubs in a network today. If you create a network, if you design a network today, it's not going to be any hubs in there. Hub is a repeater. And I'll get back to the hub, but you can't even buy hubs any longer. So if you run across any hubs, it's because you haven't got around to replacing them yet. You can't even buy hubs for home use anymore because there's switches, all of them. So, but you connect to a network device to be able to talk to other people on that LAN. There are different kinds of cables, obviously. Another cable that you use is the fiber optical cable, most commonly used for higher bandwidth. So if you have a data center in the basement of a building, you might be connecting the data center to different floors in the building using fiber optical cables. Another big advantage with using fiber is that obviously it's using optical, so light, which means that it's not as sensitive to electromagnetic pulses and stuff like that. So common with fiber optics, up to your floor plan, and then UTP, as we said, out to the users. I've got a whole chapter on Ethernet on the next chapter, so I'll just go through this real quick. An Ethernet frame, and the frame is what we call something on layer 2. And I'll go through the OSI model in another later chapter as well. But an Ethernet frame is what's used to send stuff over the Ethernet. And to start out with, the equipment we had were hubs. So what the hub do is, if I send something into an Ethernet hub, in an Ethernet frame, the hub will send that out on all ports. So every single one will get this. Now inside the frame, there's a destination and there's source. So when I receive this, the PC is going to check whether the destination MAC address, the layer 2 address, is my MAC address. If it is, I'll take care of it. If it's not for me, and I throw it away. But the hub sends data that it receives out to everyone, which is not very smart, and it's the reason why we're not using hubs today. If I want to go from my LAN, from my local area network, to another LAN, or to a van to get me some other place, I need a router, or a router, as the Americans say. Now, a router is what connects your network. So we'll talk more about this later. But if I want to connect one network to another network, there will be a router in between. And the router is the thing that keeps track of all the networks and knows if you want to send data to one network, where to find that network. So if I connect one network to another, there's going to be a router in between. And he will route between the networks. I'll get back to that later. This is a really interesting slide. I have lots of people saying, as I said earlier, We're not concerned with ATM anymore, or we're not running this, or we're not running that. We're doing everything IP. Now, that's not possible. You might be running everything application-wise using IP. You might be running voice from IP phones using IP. You might be running data from application using IP, but you cannot use only IP. Because IP, if I got a computer here, if I got a network connection to this computer, IP cannot send data over a cable. It's not capable of sending data over a cable. IP needs to go inside something else. There needs to be a layer 1, 2 technology. That technology might be Ethernet, or it might be token ring on a LAN. It might be wireless on a wireless LAN. On a WAN, it might be ATM, it could be SDH, it could be frame relay, PPP, or anything else. But an IP packet needs to go inside something else. IP don't care what that something else is, but there has to be something on the lower levels to be able to catch, to be able to transport that IP packet. So if you look at this, you'll see, if I'm a user up here and I want to send data from my PC down to this server, I can do that using whatever application, and the application is going to put the data into an IP packet. Now that IP packet, if I'm a user up here, that IP packet, I cannot send that on the cable. So in my PC, probably today, I have an Ethernet network card. So the IP packet is going to be encapsulated inside an Ethernet frame. I'll send that frame to my router over my Ethernet LAN. Now when that frame arrives at the router is going to remove the Ethernet frame. It will look into the IP packet, find out which IP address I want to go to. Obviously in this case, I want to go to this IP address the server has. It will go into his routing table, and he will find out how to best go to this IP address. Where lost the pointer. Server. Now, he will then find out that he needs to send it out on an interface. Now, if you look at this slide, it says that on the other side of this router is a WAN, and it's a frame relay service provider. We bought this from. It's a frame relay technology. So he will take your IP packet, he will encapsulate it again, this time inside a frame relay frame. He will send this frame relay frame over the frame relay, and it will arrive at this router. The router will check whether the frame is for him. If it is, he will remove the frame, look into the IP packet, take a look into the destination field and find out where this IP packet want to go. He will check his routing table to find out where he needs to send it. And in this case, he needs to send it out on a token ring network. So he will take your IP packet, he will encapsulate it again inside, in this case, a token ring frame. He will send the token ring frame to the server, and the server will check whether the frame is for him. If it is, he will remove the token ring frame. He will look into the IP packet, check whether the IP packet is supposed to go to him, and then look at what application needs to have this data, and he will send the data up to that application. So it is possible, in this case, to connect a user running an application IP-wise over Ethernet to a server running the same kind of application, or a service part of that application on IP on a totally different layer 2 technology, token ring. Now this can go on for lots of hops. Every single time you reach a router, it will remove the layer 2 frame, check the IP packet, and add a new, encapsulate the IP packet again, and send it to the next router. The next router will remove the frame, check the IP packet, and encapsulate it in a new frame. Every router, every single time. Okay? Key thing. So IP and the IP applications allow us to send data between hosts and servers or host and host. But IP needs to go into something else. IP needs to have something that carries it. I don't know if you heard that, but there's a saying that says that IP goes into something else. It has to be carried. It has to go into something else. So if you're saying you're running IP only, well, you might be running IP only because your applications, whatever they are, voice or usual data applications or video applications, are all using IP, which is fine, IP only. But IP still needs something to carry it between the different routers. So there needs to be something below IP. All right? Any questions? You okay with this? Yeah. All right. This is an example of exactly this. So in this case, you can imagine that we're trying to send FTP, File Transfer Protocol. So we're trying to send a file from one service to another, from one host to another. The FTP data is going to be in the FTP header. It's a header put there, and we'll go through that later as well, by FTP and the data. Now that FTP data, File Transfer Protocol, is using TCP as the transportation protocol. So that FTP data is going to be encapsulated by TCP, and we'll add a TCP header. And we'll talk more about TCP later as well. Now that TCP header is going to be using IP. So we're going to add an IP header, and we'll talk about that later as well, with the IP destination, the IP source, and some extra information in the IP header. Now this IP packet, all of it, is going to be encapsulated in a layer 2 frame. In this case, they're saying that the layer 2 frame is an Ethernet frame. I'll need the Ethernet frame to go from my PC to my router over that link. So we're going to have a layer 2 destination, MAC address, layer 2 address, and we're going to have a layer 2 source address, also a MAC address, obviously. And there's going to be a checksum at the end to make sure that this frame is whole. And there's going to be some other fields as well. But the key thing is that your IP packet goes inside the frame. Now, if I change this, so I go over frame relay link, I'll remove the Ethernet frame, and I'll add the frame relay frame, obviously looking different. If I get to the next router, I'll remove the frame relay frame. If it's a PPP link, I'll add the PPP frame and send it to the next router. And I'll continue changing the frame until I reach the network where the destination is. There are different kinds of protocols. And protocols is most, I used to compare with language. There are different kinds of protocols. The key thing is that we talk the same kind of protocol. I can't expect to go to Japan, for instance, if I don't know English and I don't know Japanese, because they won't understand me. And the same thing, obviously, I can't be sending IP packets to a server running IPX. Or I can't be sending Ethernet frames to a PC having a token ring network card, because we're running different protocols. Obviously, there are different protocols on different layers, but all of them is going to decide how much data can I send, how shall I send it, how's the frame or the packet, how is it made up, what fields are in there, how shall I address it, what address should I use, and how can I check whether it's complete, if it's whole, so there's no errors. Different protocols obviously do this at different levels, all of them doing obviously different things then.
One question.
Yeah.
You talk about level 2.
Yes.
The IP. Why is it level 2? Is it only a definition or
Yeah.
something
Yeah.
logic behind?
Yeah. Layer 2 is coming from the OSI model. Anyone heard about the OSI model? Yes. You can't take a Datacom course without having to go through the OSI model. It stands for Open System Interconnection. It's really easy to remember. OSI, who created OSI? Well, if you run it the other way, it's ISO. So it's the International Standards Organization that created the OSI model. And layer 2 is from the OSI model. I'll go through the OSI model in a while. We'll go through it after the Ethernet part. But layer 2 is referring to that OSI module. So Ethernet, token ring, and the other layer 2, 1, 2 technologies is in the bottom. It's what we use to go over the wire. And then IP is on layer 3, and your application is higher up. So TCP, UDP, for instance, is working on layer 4 and 5. The application is running on 5 and 6 and 7. So it's all referring back to that OSI model. So we'll go through that later on. So that's what layer 2 is coming from. It will all be clear. Promise. Another question? Good. Coming back to that thing I talked about with TCP IP and why that's still the thing that we're running. If you installed a network client, anyone running network? Anyone been running network clients? If you have, and you installed it 10 years ago, what network protocol did it install? IPX. Anyone have a Macintosh? Anyone had a Macintosh Apple? If you installed it 10, 15 years ago, what network protocol did it install? AppleTalk. If you have a Unix machine or a Linux today, perhaps, what network protocol did it install? TCP/IP. Now, most of the operation systems and the PCs and the computers, most of the operation systems had their own network protocol. Unix is coming back to the history of the Internet again. Which were the first host of mainframe computers connected to ARPANET, do you think? Well, NASA was one of them. And all the big research facilities in the US and the universities in the US. The universities were running what kind of operation system? Anyone heard of Berkeley, for instance? They were all running Unix as the operation systems. And then the people that were running ARPANET decided that we need to have a new protocol, and they started designing TCP/IP. Now, because of the universities needing to connect those networks, they were giving TCP/IP. So TCP/IP were therefore incorporated as the native network protocol for Unix. So if you're running a Unix system, it's running TCP/IP, always has been. Whereas Linux is later, but Macintosh and Windows and all of the other operation systems, they had their own network protocol. Today, because we need to be connected to the Internet, if you install a network client today, it will install TCP/IP. If you have an Apple or Macintosh, it will install TCP/IP because we need to be connected to the Internet. Now, Unix and Linux always have been. The other are doing it today because we need to be connected. If you want to send an email, now, email is sent using something called Simple Mail Transfer Protocol, SMTP. SMTP is a TCP/IP protocol. So if you want to send an email, you can't be running IPX. You need to be running TCP/IP. If you want to download a file from the internet from somewhere, from a server on the internet, you might be using FTP. Now, FTP is the TCP/IP protocol, so you need to be running TCP/IP. So, no matter what we do on the internet, it's a TCP/IP network, and all the applications and the services that you use to are all TCP/IP protocols. And obviously, we need security as well. We need firewalls to encrypt data, decrypt it. We might use tunnels, but we need to make sure that we secure our network because everyone's connected to it. Management issues. If you're management, obviously you need to be aware of adding new hardware, running different kinds of applications, security issues, as we said, and moves, adds, and changes in the network. Now, we're not supposed to be in network management, but things you need to think about when you do management. Right, any questions? I took far too much time on that chapter. I'll speed it up later. Any questions? Right, let's take the first break then. 10 minutes, please. We'll start 7 minutes past.